situation that take a vessel and pour some granular material into it, for example rice. If you dip a spoon into it, then at a certain depth of immersion, you can dip a vessel and contents by holding the spoon. Explain this phenomenon and explore the relevant parameters of the system. And we will mainly focus on the force acting on rock by rice grains under different conditions, and experimentally find relevant parameters like pressure and friction coefficient. And here is our experimental video. You can see that we can lifting up the whole system by holding the spoon. Here is our experimental setup. We use a rod, funnel, and container and pour in the rice through the funnel. And here we fix the container on the ground, and we use a force measurement to connect the rod and measuring the minimum pulling up force. For the orientation condition of operation condition, we divide it into two parts. The first one is we insert the rod at first and then pull the rice in. And we found that the rice around the rod is random orientation. But if we pull the rice in at first and then insert the rod, and the rice around the rod would be partially ordered orientation. And this break line is a weight of the whole system. So here we compare the relationship between the force and the weight. If a weight is larger than the force, we can lift up the rod. But when the force is larger than the weight, we can lift up the system. And what's the difference between these two conditions? The difference between these two conditions within aerobots is about the same. And since insert the rod first is easier to control, so we choose this method to conduct our latter experiment. And here is an observation in different depths. Since the depths increase and the contact area will increase. And here is our experimental results. We can see that since the depths increase and the force increase, so in our experimental situation, force related to contact area. For the orientation-dependent pressure and the steering constant, we use the force measurement to measure the normal force in different directions. And we define K as a horizontal force divided by vertical force, and which is equal to horizontal pressure sigma divided by vertical pressure P. And after we calculate the volume, and we found that K is about the constant is equal to 0.3. So we define 0.3 as pressure steering constant. And here is the friction in different direction. And we have two measuring methods. The first one is a grain stick on the board, which is conventional friction definition. The other one is we put 3 grains in the container, so it has internal interaction. So after our measuring, we found that the coefficient that we measure by using the method of 3 grains in the container, and the coefficient is always larger than using the first method. That's because it already considered the rice rotate. So the rice rotate will cause another torque, and it will cause a larger friction. So the coefficient that we measure will be larger. Here is a vertical pressure profile. And first, we take a part of the rice. We take a part of the rice DZ to do a force analysis. And since the rice is a kind of granular material, so it can be regarded as fluid. So we consider the upper fluid and downward fluid. We will get these two forces, and the friction from the container will give the rice a downward force, and the friction from the rock will give the rice upward force. And we also need to consider the weight of the rice. So the force equilibrium of the rice block when pull the rod up can be written as this function. And after we consider the vertical component, we will get the formula like this. And after we integrate it, we will get the pressure in different depths and Rho lambda related to radius of the container and rod, and the coefficient of the rod and container. Here is the minimum force to pull the rod up. And to pull the rod out of the rice, the force should be larger than friction force. And the friction force can be written as coefficient multiple normal force. And we rewrite normal force by the pressure. And after we rewrite this function, we will get the function of friction. And since the rice is a kind of granular material, so we need to consider the effect of a force train. And force train consists of compressed granular material that are held together, and it will generate mutual compressive force. So it will cause additional force that can predict by our theoretical model. Here is a proof of a force train. we conduct this experiment by using a rod and a container whose bottom is curved. In this situation, the rod is close to a bottom, but it isn't directly connected to it. The other one is a rod reach a bottom, and it already connected to it. So it may react to a boundary condition of a curved bottom. So the steel will cause some gap that will cause the rise to have a larger rotational angle, and it will distract the force strain. So when you distract the force strain for the situation, we will find that we can't successfully lift up the whole system in this situation. And here is a friction coefficient analysis. Since we have mentioned two kinds of measuring methods, and so we compare the theoretical line for these two parts, and we found that by using the method of free grains in a container, and the theory can predict better than using the grain stick on the board. And that's because in our experimental condition, the rice have internal force. So we need to use this. so we need to use this method. And here we can find that when the depth increase, contact area increase, and the rotational factor will be smaller, which means our experimental result will be smaller than theory predict. Here we change the shape and the perimeter of a rod. And to change the perimeter, we change the radius of the rod. So from our experimental result, we can see that since the perimeter increase, and the friction force will increase. And here is we change different shape of a holder. We use a rod and a board which have the same perimeter. And from our experimental result, we found that only perimeter will affect the friction force, and the shape won't affect it. And what's the effect of packing density? We change the packing density by knocking the whole system on the ground. So the effect of additional squeeze, it can be divided into three parts. First, it will change packing density, and it can predict by our theoretical model. When packing density increase, normal force increase, so the friction force will increase. Second, it will change the arrangement, which means the coefficient should be changed, and it will cause additional pressure on the container wall. So after we removing the squeezing force, the rice didn't return to original arrangement, so the stress still exists. And it will cause additional force than model predict. And here we can find that the experimental result is larger than theory predict, and the deviation is from we change arrangement and the additional pressure that acts on the container wall. And here we change the aspect ratio of a particle. We use a rice, mark beam, and BB shot to do this experiment. And in larger depths, the force strain will affect significantly, which means the experimental result will significantly deviate from the theoretical result. And here is a two measuring method for friction coefficient, and we found that the increasing value is rice larger than mark beam, larger than BB shots. And it can predict by the rotational torque of a rice with larger than mark beam and larger than BB shots. So we already changed the friction coefficient into the effective one. And so when the aspect ratio closer to 1, and the factor of a rotation of a particle would be smaller, so it is closer to our theoretical assumption. Here we change the radius of a container. We can see that the theory predicts that when the radius of a container is smaller, and the friction force will be bigger. And here we take the depth in 20 centimeters, for example. We found the boundary condition. When the radius of a container is smaller than 4 centimeters, that's the transmission chain is too short, so it will cause a force strain affect the experiment significantly. So the experimental result will deviate from theoretical predict. And from this part, since the radius of a container be smaller and the transmission chain be shorter, so the force strain will be affect significantly. Here we change the position of the rod, and we're describing the distance between the center of a container and the center of a rod. And since the distance increase, the friction force first decrease and then increase. And the reason that it increase is because it directly contact the wall, so the friction will be bigger. And the friction transmission chain is too long, so the pulling force of the rod can be transmitted to the container, so the friction will be reduced. And what's the factor of the spoon? We use a different folded board and a spoon to conduct this experiment, and all these four have the same contact area. So the theoretical line is the same one. And we found that when the amount fold increase and the vertical force to rise will increase, which will cause a larger friction force. So what's the effect of the spoon? First one is contact area increase. It can be predicted by a theoretical model that an area increase and friction force increase. Second, multiple folded and the turning part has a horizontal expansion component. Third, the geometry property, it will increase the equivalent volume that will shorten the distance to wall. And from here, the straightforward board and the spoon is easier, and we can easier to lift up the whole system. For the conclusion, first one, why is a critical condition for the system to lift up? And here the red line is the theoretical line for the friction between the rod and rise, and the black line is the loaded weight. So the relationship between these two is when the friction between the rod and rise is bigger than the loaded weight, the system can be lifted up. And it is like in this part, we can lift up the system. And for second, how do the friction act and influence the phenomena? And based on our theoretical model, and we also find the value of the K, and it is about 0.3, and it is pressure steering constant. And based on it, the contact area dominates regardless of the cross-section shape, and the effect of a grain shape aspect ratio described by effective friction coefficient, and breaking force chain largely reduce friction, and extra force in spoon-like shape by extra area. And that's all of my presentation. Thank you for your attention. You mean the position of a rod? Is it the same?
You have your measurement points. For each measurement point, have you used several experiments or just one experiment?
It is different experiment.
Okay, then just move on. We come to the matter. And short question. In your theory, do you assume that the rise is a fluid or a granular?
It is a regular material, so it can be regarded as a fluid.
Okay, I would disagree with as well as it was unclear in your experimental theoretical explanation, but we move on. Short question, since you used rise, have you looked at the wetness of the rise and looked at it that's all had the same wetness over all of your experiments?
Yes.
Okay, thank you. And if you move on, how did you or with what did you exert the force on your rod? Based only by hand and then measured the force which was exerted on the rod to add your force to sensor that you used a different method?
I have used a rod to conduct the force measurement and to measure the minimally pick up force, and I think our force measurement.
You exerted with what you exerted the force on the rod by hand or with this third mechanism?
Oh yes, by hand.
Okay, thank you. I would say there would be better for that, especially because we can really set a specific force you can take on it. Never slightly change your.
Excuse me, I don't want to interrupt. This is a question, it's not a discussion.
Sorry, okay, but just move on. So is it possible, just in your case, is it possible to achieve a lift without friction inside your system?
You mean the friction between what?
Okay, we just move on.
Could you please speak slowly?
We just move on. We just move on.
Okay, we move into components, preparation time, and remember to allow time to just
没有都听得懂吗？你把耳机拔下来好吗？
对。
把耳机让我都听得到，然后这样我才能播声音出来。然后，等一下，他第一个问你是说你一个实验做几次，做一次还是做很多次？ 然后第二个问题我忘记了，然后第三个问题是问你说你是考虑 granular 还是 fluent？对，然后他说他 disagree with you，因为你刚才说你觉得你可以看成一个 fluent， 对，所以你要解释一下。然后对，就有点太还好，有点紧张，我应该还好。
那坐我隔壁好。
我坐他隔壁好，他听不懂。
是不是可以把声音播出来？
对，可以。
后面的问题我好像没有。
你播声音。
我播声音。
然后
他第一个问题是问你一次还是很多次吗？
是，然后你等一下如果听不懂的话，你不要去看我们，你就叫他再重问一次就好。然后叫他讲慢一点。对，然后我如果知道他要问什么话，你要回答什么，我就放你前面，我不用转头看你。然后你这个可以。然后你叫他重新讲一次，或是怎么样。然后你讲大概就然后第一个。就是什么？你一个点要测几次
5次。
10次。好。
那我那 A 5的都很小哎。
这不是很小。
他有人问我说是不是用手？
那个没差。
你用拉力读书机就没有关系。
你就跟他说，但是你还是有测出你用拉力读书机是多少，因为他刚才可能以为你只有用手而已，然后你要跟他说你会用手。
他说我刚才给他看过什么？
没有，你刚才完全没有 share 你知道。
是哦。
对，所以好没关系，就是被说。
好笑。我刚没 share 我就觉得。
好啊，不重要。
一切安好。
所以。
但是我要 share 的话，我是要再按一次那个。
不是，他等下会给你 permission。
所以，是我刚没有转这个钱。
然后你听不懂就叫他 rephrase， 或者叫再讲一次。然后 use the force interview on 10， 就不要录到force lifting 因为他等下如果再问一次的话，就讲。有听到？那等下如果问你这个话，就讲。
一切安好。话给说出来吧。
不用。
就他到底会当成这里？他到底会当成6题？我觉得大概是时候，就是他是真心的，是可以让。
没有，你等下就跟他说，你在让打之前都是有做的调整，但是要让他知道，然后你就说你考虑的是granular吧。
哦。
然后就是你在让打之下的话，因为让打之前对。好，我等下直接，我直接写给你。
看发音收掉。
没有放什么卷上饭。
就是
没有放。
有点熟悉。对啊，我们做法律。
主要他就是做法律的。
Okay, so when I make a presentation, I will do the position on.
Just pause a moment. Okay, you're ready to start. Can we just make sure the timer's started by Tony? You have 4 minutes of content for discussion.
You're ready to start? Okay, so Yeah, I'm doing the opposition on problem number 12, rise kettlebells today. So if we move on to the report at first, that had a really clear communication, as well, especially on the report structure, so it was quite easy and clear to follow in completely, as well as like as well as if we go on to the report itself, there's a significant ideas, especially for example that at the beginning she showed us first, okay, she checked between different two sides, so if you just put the vessel inside it first and then put mineral material on it, or if you just put mineral material inside and then put the spoon inside, and show that she had a lot of experimental results inside the report, which really contributed to the report as whole. Now, if we go on, like I already said, with the vessel, and I want to put inside, we can say that it's a bit out of sight of the task, since the spoon itself says if you dip the spoon afterwards in it. But I think that in all it doesn't have the huge impact, but it's clearly not completely what the task there. Now, for example, if you then go to the theoretical approaches, we can say that there is some inconsistency to which we will then come later. Okay, now if you go to the experiment, we say it was really, especially this measurements for the friction, or the friction, the aesthetic friction between the grains and the rod was really nicely done, and we can really say that this was a good job where the reporter did that. As well as that she, for example, changed a lot of parameters, which is in that way really good, but for example, some other parameters were not investigated. For example, also the tilting angle of the spoon, which would be really be interesting, for example, also to see if the reporter showed that it's always for all experiments the same. Now, for example, if we go on to the reproducibility, we can say that like already the angle was a bit unclear, and therefore we can say we have already an inaccuracy there. Now, if we go on, for example, that if she applies the force by hand onto the vessel, we can say that this was never
好吧，不要。
that all the forces she showed us for the friction force are really the same forces, so that if she just used, for example, just pulls sometimes stronger, sometimes weaker, and therefore also creating a real inaccuracy. As well as that, for example, the time in which she lifted over the time period she lifted the vessel was not investigated, and it also makes a difference if she, for example, just pull it really fastly or slowly pull it, and that's also what we will discuss later inside the opposition. Now, if we move on to the theory, we can say that she used the theoretical model looking at the forces of the static friction as well as of the force of the static friction. Well, it really could mainly only show us a qualitative explanation or a qualitative trend for the model, but always had some real deviations, which she always explained on the chain forces, but on the other hand, she didn't try it even, or she hasn't she hadn't investigated this further, so just said that she has chain forces which then get task these deviations, but it didn't really investigate, for example, how she could explain these force changes theoretically. As well as she stated that she explained the material, for which she said it's only with that she gets force changes, and then assumed it's a fluid, which contradicts itself. So we can say that we have an inconsistency in this theoretical approach. Exactly. As well as that she, if you go on, for example, that the rise, if we have a spoon, for example, we will have on top of the spoon at some points rise laying on it, and therefore also creating a pressure downward, which was not really necessary. But if you now take and complete it, we can say the task was only partially fulfilled. For example, the explanation of this phenomenon was really nicely done, but for example, at the beginning she dipped at first the spoon and not at first the granular material. And I think we're almost coming to the end of my presentation, so we will move on to the positions. Therefore, I'd like to invite the reporter on the stage. Exactly. So,
Okay.
my first question would be: it was a bit unclear inside your report if you just slowly, for example, slowly put slowly apply the force on the vessel, or if you just rapidly.
Can I show my presentation? Okay. Can I get permission to show my presentation? And here we're measuring the the friction force, and here is a force, and by using the force measurement, and we can get the maximum pulling up force. So this dot is for the rod just move. So it doesn't relate to and how fast or how slowly that we're pulling up the force. In all conditions we can get the maximum friction force, and it's a rod just move. So this is a friction force that we measure.
So you just slowly pull it upwards and just look when the rod moves.
And yes.
Very good. Okay. So how long did you slowly increase the pressure? Did I got it right? On which time scale we can expect that you slowly increase the pressure? So did you just go like, okay, I do it something like that, or just you increase slowly, waited 10 seconds and then increase later? So what was the time period of that?
You mean the pulling up time? It is about 5 seconds.
So you applied one force, waited 5 seconds, then applied the second force. The high force, if it does not fall down.
You mean if we stick the container on the ground, or you mean we need to lifting up the whole system?
Well, because what I would expect, I mean just the lifting of the vessel, because what I would expect is that if you get to the point where you are slightly over the static friction of due to the granule inside, then you would have just a slowly sliding of the vessel, which should take a longer time period.
So you mean it have a slow sliding? So we already consider it in our friction coefficient measurement, because it is like the internal force of the rise.
We will move on. And what I want you to ask is to your force chains. Is it like that you just have one force chain, and if you move higher, will you just break one up the force chains, or does something change over time there?
The force chain is related to the transmission transmission length. So if you mean the effect of the force chain, or how?
Okay. Maybe in other terms, can you show us the force over time if you just put out the vessel? So if you.
You mean this part?
Yeah, could you please make it bigger? I can't recognize a lot of them. Thank you. So, what can we see here? So we have the force over the time scale, and upwards is the force.
Yes.
Why does the force get negative? Can you explain us that at first?
And for our force measurement, and here we can see that we use a line to connect the rod and the force measurement. So the force will give it a downward direction, but the direction it didn't relate to it. So it is negatively mounted. Could you speak again?
Okay, could you please get whiteboard back so that we draw a bit?
Whiteboard. Oh, yes, here.
Okay, so maybe let me draw it also. Just activate it, I can draw.
Oh.
Step and draw. Should be in the middle, some button with the screen.
Thank you.
Good. Okay, so how I understood it is that how you did it in your measurement is that you slowly increase, and then if you put out, if the vessel starts to move out, you always apply the same force.
Yes.
When it starts sliding outwards. Okay, how does the force acting onto the vessel due to the granule looks like over time then, if you put it slowly outwards?
You mean the force and the time? And
yeah, but I mean the force of the granule putting it onto the vessel, trying to hold it down.
It may be decreased by time. Yes. and maybe it is the direction of the friction from the container is a downward direction. So maybe it's like this.
Okay, but if you go here back, is it really a clear line, or can you see, for example, some oscillations?
Could you speak again?
Is this force going downwards over time? Is it a clear line, or is it oscillates a bit?
And I think it's a curve, or maybe it's not. And since our measurement, you can see that it's like a curve. So the friction force from the container, it also should be like a curve.
Because what I would expect is that if you say it's due to chain forces, that you need to break up. So what I would expect to is that if you have your chain force and you slowly pull it upwards, then the force is. So what happens is that the chains try to make a force, and if you move higher, the chains will have a pressure exerted on it, and therefore they would be exerted a higher force, and therefore resulting in a higher force trying to pull back. But what then happens if there is one breakdown, the force chain will break, and later on you will just have a short time of movement, and then a new force chain would occur, and therefore I would expect that you should have like small oscillations.
And I think for this part it is related to radius of a container. If the radius of a container become bigger and the force chain will be, and the influence of the force chain will be smaller, so maybe we won't have the situation that it's being said. But if the radius of container becomes smaller, then I agree with you.
But you don't agree with me that if the radius of the container is bigger?
Yes, because the character of the friction force from the container will not be that significantly because the force chain related to the transmission length. So it will cause some. Yes.
I didn't get it completely, but in my understanding of the phenomenon is that if you just have the force bridges over time and you pull it slightly out, what happens if one breaks, and therefore you have a slower force trying to acting downwards, and then it will, but I think we just move on. And short question, can you explain us what the difference is between such a container in the use or from the shape of the container which looks something like that? Would you see a difference if you have all of the other parameters the same?
And I think because this wall will give it a force like in this direction, so it will cause the granular material become more tightly. So when it becomes tightly, the friction force that we need will be smaller that can lifting up the whole system. So it will be more successfully. The successful condition will be more easily to reach.
Rather if it has like a form like that. So that way that thing works better. So just yes. So you agree that this container would work better?
Yes.
Okay. Okay, I can agree on that. With you on that. I would say that in your theory, that's not included at all. So we have a problem. Your theory would predict both of the containers would have the same force pressure that backwards. Am I right?
My theory didn't consider the upper part. If we need to consider the upper part and the function of the pressure should be rewrite. Since it will cause another friction force.
Okay, I can agree on that. So your theory does not, for example, include the shape, and therefore we had, for example, that interesting case is not included in the theory. Okay. To move on, if I ask you what would happen, sorry, I have to put a bit out of focus. Yeah. So if you it was a bit of my focus. You showed us that you use, for example, different densities for your rise rate. How did you achieve that?
I change density by knocking the whole system on the ground. So we can see that in the same weight and the volume will be smaller. So the volume will be smaller, the packing density will be bigger. That's because we knocking the whole system.
Push the whole rise downwards.
Yes, we knocking the whole system on the ground. So it will cause additional squeezing force.
Okay, yeah, I can agree on that, but I will also say that therefore you increase the density itself. Okay, yes. Let's try a summary of the solution. So at the beginning we looked at, for example, the experimental setup and we investigated how she built the vessel. And I would say it's, for example, important that what she did investigate is that there's a difference if you just quickly pull it out or if you just slowly pull it out. She only investigated the case where she slowly pulled it out. And therefore we can say it's nice to have the golden case, but it also would be nice to investigate the case where you just strongly or fast pulling out, because then there's force strength would be higher, therefore creating a higher repelling force. As well as we can say that this force shape will slow up and will over time will have smaller effect, but will degrade in the force over time because they will slip partly, and therefore I would say it would be important to look, for example, for a longer period of time. Like we also show now in the end that she also has some kind of inconsistency in theory as well as some kind of inconsistency in theory, so we can move on.
Thank you very much. Move on to the concluding remarks of the report.
And first, every experiment we have conducted 10 times for accuracy, and we have used a force meter to obtain the force while lifting up the force, and the maximum force that needed to pull was collected. So our measurement method is very accuracy, and the order of a material and the rod isn't significant. So the effect on the pressure is the main focus, and the small rotation will affecting unsteady friction was considered while measuring, and by substituting different integration equation, our theory can adapt every condition of vessel and for the granular material. And we have considered granular material. However, we have calculated the value of lambda. So when the depth is smaller than lambda, and the pressure and the depth is positive correlation, so it can be regarded as fluid. And that's all of my closing remark. And thank you.
Move on this stage to bring in the jury and get jury questions. So if I can ask the teams to put down their video for the moment and the jurors to step up so we can see them. And the reporter and opponent, please stay.
为什么不照规则？
Yeah, thank you. Okay, so we move on. We have time for questions. Is there anyone who would like to start this off?
你两个问题啊，大家看我们 get the permission to share.
I would
like to ask a question to the reporter about the way you measured. About the way you measured the friction coefficient. So how did you measure the tangential force acting on the rod?
对不起。
To the report.
We measure the coefficient. We measure the coefficient by using a container on the slope, and then we directly to lifting up the slope and measure the maximum angle that the minimum angle that the container start to move. So it is the maximum static friction coefficient.
That's good.
Answers that. Other questions?
Oh yeah, I want to ask the reporter. The opponent pointed out your theoretical model is insufficient to explain the phenomena. For example, the friction, the force change should be considered. What do you think at the moment? You are thinking the force change is negligible or that is important?
I think our theoretical model can predict some specific condition, like if in a big radius of a container, it can predict well. But in a small radius, in a smaller radius, which you consider the force strain, since the transmission length becomes smaller, so the effect of the force strain will be significantly, and it can't be ignored.
Can you estimate the critical radius?
It's about 4 centimeters.
Okay.
Yes.
Okay, thank you. Can I ask the opponent a question? You've talked a lot about the speed of pulling, so whether it's a quick. What exactly do you think is the main physical difference in doing it fast or slow?
Well, I would expect that the difference is that if you do it really fast, then you have this force change which develop over time. And if you do it just fast enough, that you can press this force changes together, and therefore, because what I would expect is that the force will break up if it slowly slips apart. And if you just really fast and it's not tight, that the force chain will slip apart, and therefore I would expect that the force chain will get stronger than if you just slowly pull it outwards.
If you're pulling it quickly, have you got control of that size of force? If you're really pulling it up quickly, do you measure the exact instant of the force easily?
So I would say if you don't do it by hand, for example, but for example you can add on the bottom, for example, a certain weight, and then just put for example, make a system where we just put weight under it, and then just like take away the point where you hold your weight, and therefore just let it fall down with weight. Then you can have really a consistent force over the time which pulls downwards. But not by hand. Of course, by hand it wouldn't work.
So just to the reporter, the same sort of question really. Do you think a quick pull or a slow pull is important? Is different?
And I think the slower puller is more important, because if we pull it more quickly, and it didn't have enough time to contact with the granular material, so if we lift it up quickly, and we only can lift up the rod, but if we slowly and it have more time to connect, so the effect of a granular material is related to the contact area, and so the contact area will cause us easier to lifting up the whole system.
应该超紧张的。
真的哦？
哇，你讲话一直讲2个字讲得行吗？许医生拖时间都没有这么厉害，许医生拖时间都没有你这么厉害。现在还笑得出来？应该待会笑得出来，应该待会。为什么你不照着我写的？
等一下就笑得出来。
差不多啊，我应该变得差不多啊。
最后加了一个，那个纳粹跟没有纳粹差很多。纳粹可以跟那可差。现在纳粹不能差。我后面是写纳粹。写了。我后面是写说。下一个。现在笑不出来。